All right, so this is the first part of section 11.5, and we're learning about lines in space.
What? Don't worry about it.
So by now we've all done a lot of work with lines in the plane and how we analyze lines in the plane using slope, and we've used slope for a lot of different things in a lot of different contexts. But in space, we're going to use vectors to describe lines, because slope really in space, slope really doesn't. You can't analyze the lines in the same way, because you can talk about the slope in all kinds of different ways. So what we're going to do is, let's draw a coordinate system here first. So our standard three-dimensional coordinate system. And we're going to start with a vector down here. And we'll put this vector in standard position. We'll call this vector V. And we'll say that V equals it's just some arbitrary vector A, B, C. And we have a line up above here, and we're going to say that our line, put two arrows on my line. So there's my line. This is line L. And point P is on line L. P is, we'll call it x1, y1, z1. And point Q is also on this line. And it's just some arbitrary point x, y, and z. And so line L is through point P and Q. And L is parallel to vector V. We call this vector, so this is a setup for how we're going to analyze lines in space. We'll have a vector that our line is parallel to. We call this vector the direction vector for the line. So it just this just tells us the direction of the line, because our line is parallel to this vector. And we call A, B, and C, the components of V, are the direction numbers for the line. So as we're working with lines in space, will be the direction numbers, the direction vector will be important quantities. So this is our setup. So we're going to define a line in space. And the nice thing about a definition is that, like I said, once you make it your definition, as long as it makes sense, as long as the mathematics behind it makes sense, then you just go with your definition. You make that your definition, then you're set. So we're going to define L as the set of all points Q, and Q is just some arbitrary point on our line, such that vector PQ is parallel to our direction vector. So this is how we're going to define a line in space. we'll define it as a set of all points Q such that if we're given some point, that the vector from P to Q is parallel to our direction vector. So what this tells us is that PQ, vector PQ, is a scalar multiple of V. So PQ equals some scalar T times V, where T is a scalar. This is the vector equation for a line. So we have this nice clean expression for a line in space. All we need are the points Q such that the vector PQ, we have a point P, our vector PQ is a scalar multiple of our direction vector. Now we're going to work with this vector equation to come up with some other expressions for a line in space that are a little easier to work with. So I'm going to write this out in terms of P, the point P that we defined up here, and the point Q that we defined up here. And we're going to work with those points and come up with a more useful expression. So let's look at that. So we're going to say that PQ, since PQ is a scalar multiple of V, I'm going to say that PQ is x minus x1, y minus y1, z minus z1. That's our expression for PQ in terms of the points, and that equals T, some scalar multiple times our direction vector ABC. And what we're going to do now is equate components. So if we equate components and rearrange just a little bit, I get that x equals x1 minus at, y equals y1 minus bt. I'm sorry, this should be a plus, and z equals z1 plus ct. So we equate our components. This gives us the standard equations or parametric equations for a line in space. So we equate the components of these two vectors, and this gives us a set of parametric equations for a line in space. And this form is going to be the one that we use probably most often. And just to be clear, from these equations, L, our line, L passes through the point x1, y1, z1. And is parallel to the vector ABC. So when we have our parametric equations, we can see a point that our line passes through, and we can see the components of the vector that our line is parallel to. Now we can manipulate these a little more. We can solve each of these equations for t. So we're going to eliminate the parameter, solve each equation for t. So this should be parallel. There we go. So we're going to eliminate the parameter. And we get that x minus x1 over a equals y minus y1 over b, and that equals z minus z1 over c.
Is the law of sines related to this somehow?
I don't think so.
Okay, so it's the same kind
It's
of
same kind of form, right? And we call these the symmetric equations. And again, the line goes through x1, y1, z1, and it's parallel to the vector a, b, c. So all we did here was solve each equation for t, and then we can set each pair of equations equal to each other. So questions on our development here, how we talk about a line in space. Does it make sense defining a line that way? Yeah? Okay, let's look at a couple of examples and then we'll talk about how we find distance from a point to a line. That's another thing that we're often interested in. How far away are we from this line? So a couple of examples. So we want the parametric and symmetric equations for the line through this point, negative 2, 0, 4. And we'll start off with a really easy example, and it's parallel to our vector 2, 4, negative 2. So our direction numbers come from our vector that our line is to which our line is parallel. So the direction numbers. Yes. So our direction numbers. A equals 2. B equals 4, and C equals negative 2. And I can just, the points, I'm just making this all explicit for this example. The points, we're going to say that x1 equals negative 2, the point that we go through, y1 equals 0, and z1 equals 4. So we're just going to plug these into our form for our equation. So our parametric equations, x equals minus 2 plus 2t, y equals 0 plus 4t, and z equals 4 minus 2t. And we solve each equation for t to get our symmetric equations. We get x plus 2 over 2 equals y over 4 equals negative z minus 4 over 2. And those would be our symmetric equations. Questions on that? So if we know our vector, we know our points, then we're just plugging into our equation. So this one was a really easy example. All right, let's look at one that takes a little more work. So we want the parametric equations for the line through P.1 is -3 to -3, and Q is the point 1, -1, 4. So we need a couple of things here. We need to find our direction numbers, and we need to find we need to pick one point on the line. We have 2 points on the line, so we can pick either of those for our x1, y1, z1. How are we going to get our direction numbers? Q minus P, and what did you say, Cole?
Just find the vector.
Just find the vector from P to Q. So we can say that PQ, the vector PQ, is parallel to our line. So that can be our direction vector. So we're going to say PQ, when I come up with the components for PQ, PQ is 4, -3, 7. So our direction numbers, this gives me, my direction numbers A equals 4, B equals -3, and C equals 7 for my direction numbers. And I'm going to choose point P, I could choose point Q as well. So let P be our point x1, y1, z1. And then I can write my parametric equations using this point and these direction numbers. So I can write x equals -3 plus 4t, y equals 2 minus 3t, and z equals -3 plus 7t. And those are my parametric equations for our line. We could have chosen Q for our initial point, and we would get a slightly different expression for our line. It would still be parametric equations for our line. So just like we talked about before with parametric equations, the parametric equations for a line are not unique. So questions on that? Finding our equations for a line, generally pretty easy. All right, let's talk about how we find the distance from a point to a line. So I'll start out with a diagram here, and we will come up with a way to find the distance from a point to a line. So here is our line. This way. So there's our line, and here's our point Q up here. So we want the distance from Q to our line. So what we need to do is I'm going to drop this down like so. We're looking for this perpendicular distance. Here. So this is the distance that I'm looking for. Anybody have an idea of how we might do this? What we might want to do? Thinking about what we've been working on in the last couple of days. It has something to do with a vector in Q. So let me do something else. Let me draw a point. Here, we're getting on the right track. So, yes, it has something to do with the cross product. So here's my point P on my line. Let's connect point P and Q. Let's make a vector from P to Q. So I'm going to do this. Question, Anna? Oops. I want that to be solid. So let's connect P and Q. There's my vector PQ. And I'm going to say that I have a direction vector. I have a point P on the line. Let's draw in our direction vector for the line as well. So here's there's my direction vector for the line. And we'll call that vector U. Let me put this, I'm going to put U underneath here because I want something else to go there. So there's my direction vector. P is on the line. And U is a direction vector. And that's PQ. So let's draw in our angle here between the line and PQ. What's the length, what's the distance in terms of this triangle? What's this D in terms of my triangle that I drew? D, the distance is the magnitude of PQ times the sine of theta. Well, the magnitude of PQ times the sine of theta is what? In terms of something that we've been working with before. It's part of the cross product, right? The magnitude of PQ sine theta is equal to the magnitude of PQ cross U over the length of U. Because the magnitude of PQ cross theta, or cross U, is PQ, the magnitude of PQ times the magnitude of U times the sine of the angle between the two vectors. So so this distance, and this equals D. So the distance between a point and a line is given by this expression, the magnitude of PQ cross U over the length of U. So that's the expression that we're looking for. So to find the distance between a point and a line, we pick a point on our line, form the vector from P to the point that we're interested in, take the cross product of that vector with our direction vector, and divide by the length of the direction vector. And that gives us our distance. So when we're finding the distance between a point and a line, we're using the cross product. Does that make sense? And next week when we come back, we'll work with planes. And when we work with planes, our distance turns out to involve the dot product.
The homework all involves plane work.
Did I?
305, 35, 39, 43. 35 is equation of the plane passing the point.
Oh, that's right. That's for Monday. You're one day ahead.
Fair me.
So this is our expression using our analysis for how we write the equation of a line. This is our expression for the distance between a point and a line. So let's do a couple of examples with Well, let's do an example with that, and then we'll be done. All right, so we want to find the distance from the point Q, which is 1, 1, 5, to our line, given by x equals 1 plus t, y equals 3 minus t, and z equals 2t. So to find our distance, we need a couple of things. We need to find a point on our line to construct our vector PQ, and we need to know our direction vector. Because we need to make that cross product with PQ and our direction vector. So how can we find a point on our line? And so Cole says 1, 1, 3, 2. So what? 1, 3, 0. So what are we doing?
For the equation.
Just substitute a value of t for a parameter into our equation. Let t equal 0. So if we let t equal 0, we get a point on the line is 1, 3, 0. So I can just pick any value of my parameter and get a point on the line. So I can any value I plug in here is going to give me a point x, y, and z that's on my line. So there is my point on the line, and we need our direction vector. So from our equations, what is our direction vector? 1, negative 1, 2. It's just the coefficients in front of my parameter. 1, negative 1, 2. So that's my direction vector for the line. And our direction numbers, you don't have to write the direction numbers if it helps you remember, just because we wrote our formulas. In terms of the direction number, A equals 1, B equals negative 1, and C equals 2 for our direction numbers. And our distance is PQ, the magnitude of PQ cross V divided by the length of V. So what is going to be our vector PQ? We have a point. We have 2 points. So PQ is going to be what? Zero, negative 2, 5. So we just construct the vector from P to Q. PQ is 0, negative 2, 5. Then we form our cross product, divide by the length of our vector. So PQ cross V is our determinant here. 0, negative 2, 5. And V is 1, negative 1, 2. When we find our cross product, it turns out that it is I plus 5j plus 2k. And the magnitude of V is the square root of 6, using vector V here. So our distance is, and we need the magnitude of PQ cross V. The magnitude of PQ cross V is the square root of 30 from this vector. So our distance is the square root of 30 over the square root of 6, and that is the square root of 5. So we have square root of 5 units between between this point and our line. Yeah. A quick way to find the magnitude of PQ cross V, other than actually doing the cross product and finding the magnitude. Actually going through this, I'm not aware of that. So you actually have to do the cross product and then actually find the magnitude. I'm not aware of a quick way to do it. Questions on that? All right. So we're finally with vectors. We're starting to get liberated from the plane. We're moving into space, and we can talk about lines in space. On Monday we'll talk about planes in space, and then we'll start talking about surfaces in space, and that's when things start getting really interesting. And a big part of second semester is going to be relating lines and planes to surfaces, because we're going to be interested in, when we're talking about a surface, rather than a tangent line, we're going to be interested in the tangent plane. When we talk about the intersection of surfaces, we are interested in a line that is tangent to the curve of intersection. So we're going to be doing some very interesting things with lines and planes in space. All right, homework. And let's make sure the homework is about lines and not about planes. All right, there you go.